Welcome to Calculus 3. This is Integration and Multivariable Calculus. This is sections 13.1 and 13.2. This is the first of a two-part video. This video will talk about the theory behind the integration, and the second video will talk through several examples. So recalling Calculus 1, when we were talking about integration in the area but under curves, we looked at drawing little rectangles and adding up the sum of the area of the little rectangles. So the area under the curve f of x was equal to the integral from a to b of the function f of x with respect to x. In multivariable calculus, we have a similar idea. Given that we have a surface f of xy, we take rectangular solids, here indicated as blue, over a region R, and we take the volume is equal to the double integral over the region R of the function f of xy with respect to the area of the solids, where we have that the area, the little change in area, we can think of as a little square with dy dx as a little change. So we know that for at least the xy coordinate system, that dy dx will relate to the change in area. This could change depending on our coordinate system. So let's look at a quick example. So suppose that we have the double integral from 0 to 2 of the integral -1 to 1 of x minus y with respect to y with respect to x. So let's break this down. So our region here looks like y, which is the inside integral, goes from the values -1 to 1. This is because if I look at my inside integral, just like derivatives, you can think of this as kind of a nested operation. The inside piece is with respect to y, and then the outside piece, the resultant, is respect to x. So y is a function from -1 to 1, it has its bounds, and x has bounds from 0 to 2. So our region of integration, if we were to draw this on the xy plane, looking at our shadow, we have y is bounded from -1 to 1, and x is bounded from 0 to 2. So our region of integration looks like a little box here. So in our rectangles, we're drawing our boxes with respect to y first, and then with respect to x. So we're allowing our y's to change, and then allowing our x's to change. So our y is changing first, so our rectangles look like they're going sideways in our region with respect to y. So as we solve this integral, we can think about it as the inside function first. And so if we look at the inside, we're looking at the function -1 to 1, integral from -1 to 1 of x minus y with respect to y. And just like with derivatives, here x is a constant because it is not with respect to y, so we treat x just as the number 1, like the number 3 rather. And so when we integrate this, we get xy minus 1/2 y squared, evaluated from -1 to 1 using the fundamental theorem of calculus. We see that we get x times 1 minus 1/2 1 squared times 1 squared. This is our first part of the fundamental theorem of calculus, minus x times -1 minus 1/2 times -1 squared, which results to 2x, because the -1/2s cancel. This turns into -1/2, and this turns into +1/2, and those cancel each other out. And so now our outside integral looks like from 0 to 2. That was our original x bounds. We take our inside integral and we drop it in, so here's our 2x, and this is with respect to x. And now we evaluate this just as before, so we get x squared, evaluated from 0 to 2, so we easily see that this is 2 squared minus 0 squared, which is equal to 4. So the area over this region, excuse me, the volume over this region is equal to 4 units. So the question is what if we had done this the other way? What if we had looked at the rectangles vertically? And the question is it possible to switch the bounds? If it's possible to switch the bounds on the rectangles, so if we had our same region of integration from 0 to 2 for our x, and from -1 to 1 for our y, would we get the same volume if we looked at our rectangles vertically? And it turns out that so long as we preserve the region and describe the region in the same way, we do in fact get the same volume. And this is what we know as Fubini's theorem in the general form. So your book talks about Fubini's theorem in 2 forms. I'm going to present just the general form as a way of making it a little easier to understand rather than presenting 2 different forms first. So Fubini's theorem in the general form says let the function f of xy be continuous on a region R if the region is defined where x is a constant first and y is a function of x as its bounds. So with this drawing, we can think of the function here as, let's draw our axes here. We have some curve here. We'll just do it in dimensions here. So x is constant. And we have y as a function. Here's my upper bound, g2. And in my lower bound, g1. So here y is a function of x. My bounds on y, functions g1 and g2. And I'm looking at the region, and my region is defined to be this area between A and B, bounded by g1 and g2. Then my double integral over the region R of my surface with respect to that area is equal to the double integral with the constant on the outside of g1 and g2. So the integral from a to b of the integral from the function g1 of x, g2 of x, of the surface, the function f of xy, with respect to y, with respect to x. It's important to note that the y is a function of x. So x must be used in the integral before you take it with respect to that variable. Now, if the region is defined where x is a function of y, so we have a corresponding picture here where our rectangles, our intervals here, c and d, y is a function where that's constant. So we have kind of our constant bounds here as y, but our rectangles x. Here's our functions h1 and h2 as a function of x. And again, here's our region R. R in here. Then the function f of xy with respect to the area is equal to the constant bounds on the outside with respect to the functions of y on the inside, dx, dy. No, sorry, drop the function. The function of f of xy, dx, dy. So Fubini's theorem says that depending on the order that you draw the region, depending on the way you draw the region, that you can choose to integrate with respect to x first or integrate with respect to y. The key point with Fubini's theorem is that you have to preserve the region. So the key point is you can switch your bounds around so long as you preserve the region. If you don't preserve the region, then you are no longer integrating over the same area, and thus your answer may be wrong. So let's return to the previous example. So if we consider again the example 0 to 2, -1 to 1 of x minus y dy dx, we said the region R looked like the rectangle from -1 to 1 for our y-axis and 0 to 2 for our x-axis before we had drawn the rectangles horizontally. But now if we draw the rectangles vertically, we're allowing x to change first. So if we allow x to change from 0 to 2, and y is still changing from -1 to 1, we can rewrite our integral as y is now our constant on the outside, and we can think of x as a function of y, where these are our h1 and our h2. Even though they're constants, we can still think of them as functions of y. And then we preserve our inside surface, dx, dy, and we can check. We see that we get the integral from -1 to 1 of x squared minus xy, evaluated from 0 to 2, dy. So combining kind of the outside and inside piece is a different way of visualizing this. So we get 4 minus 2y dy. So we get 4y minus y squared, evaluated from -1 to 1. So we get 4 minus 1 minus -4 plus, excuse me, I dropped a 1/2 somewhere. I dropped a 1/2 right here. So we should have x squared over 2. So this should be a 2 minus 2y. And this gives us a 2, and this should give us 2 minus 1 minus -2 minus 1, which gives us 4, as we expect. So this tells us that so long as we preserve the region, that the order of the integration doesn't matter. So the next video will give 2 more examples of integration with multivariable calculus, and this will be followed by a 3rd video introducing polar coordinates and showing how we can use different coordinate systems with integration.